Hi, this is Andrew McLaren here. We're going to go over dimensional analysis. This video is intended for people who want to understand the math behind the procedure. So if you want to skip to the procedure, that is kind of the train tracks method. Um, I really want to work on helping you understand this though. So we're going to spend a little bit of time going over like what it means to convert. And what I mean by multiplying by one is explaining some of the math here and canceling out units. I wanted to explain what that really means. We're going to do that by looking at some graphs, tables, and equations. And then we will get to the point where we're able to just convert from one thing to another. Or if you need to convert from one thing to something in the middle to a third thing, we'll also be able to do that, or a fourth or a fifth or a sixth. That's the power of the train track method. When we convert, we're taking one thing and turning it into the equivalent or equal amounts of a different thing. It could also be two different aspects of the same thing. So if I'm walking in a line and I'm traveling 2 meters per second, I can graph that out as a very simple table right here. So you can kind of see that essentially each second that goes by, I'm going up by 2 meters. So this is a nice linear relationship. So just reminding you, linear relationships look something like that. And I'm not going to put all the units on this. That's not really what we're doing right now. The main idea here is if you know some time, you should be able to say what the position is. You can convert between time to position. So that's kind of what we're doing here is we're converting. And that's kind of what's happening here as well, as you're doing that conversion, right? So you've got like that process of changing from one thing or one aspect of it into a different aspect of it. So if I wanted to look at this in terms of a linear equation, I've got y is equal to mx plus b. In this graph, it looks like it goes up by 2 every time x goes up by 1. So this is a slope of 2. And this is actually going to be of the units 2 meters per second. So that's our m value right there. And that's times x. So we've got this formula for this relationship. And we can plug in x that say x is equal to 3 seconds. So that we've got our 2 meters per second, and that's going to be equal to y. So there isn't any y-intercept because we're starting at 0. But the main idea here is that when you have this m, that's where that conversion is happening. It's converting between seconds and meters. So a conversion factor needs to have one unit on top and bottom, and it should cancel out. And we'll go over this a lot more in the later part of the video. It's called canceling out units, right? But we are left with just meters. And so we now know that y is equal to 6 meters. And this was when x was equal to 3 seconds. So we were able to convert between meters and seconds there. In most of the time when you're looking at this, it's written just as like this times that. But I want to give this that reference frame of a linear equation because it does help you think about what we're doing when we're doing conversions. I'm going to do a few more of these. If you'd like to skip ahead, feel free. But I just wanted to drill home this point. So you could have some total cost that you're trying to spend at a store, cost per unit, and number of units. So let's say it's going to cost like $3 per, I don't know, let's say apple. So this is $3 per apple. And let's say you have like $60 and you're asked, well, how many apples can you get with that? You might be able to do that math in your head. You could also think about this as a linear relationship where you have the apples and the cost. And so this slope right here, this m, that's equal to the $3 per apple. And just a reminder, when you say per, you could write it like next to it and then you do like the dash, or you could say apples like underneath in the denominator. The reason it's in the denominator is because, well, we're canceling out that unit. We're converting. And if we look at this, I think I might need a second to make my own new table. But essentially, we have a similar looking table here. But instead of time and position, we're going to have apples and cost. And this would be dollars. And this doesn't really have a unit because we know what an apple is. And it should go up $3 each time we get a new apple. So we kind of get across this idea that there's a relationship between the cost and the number of apples that you've bought. And you could write that out as a linear equation again. So this is that y is equal to mx plus b. And then we've got, in this case, this is that $3 per apple. And we're multiplying that by, let's say that you've got, in this problem, we're given the cost. And so we can say, okay, well, this is going to cost $60. And I want to know how much, how many apples that is. And so we can divide both sides by 3. And I'm just going to do a little, because I wanted to bring our units with us, I'm going to just bring this down like that. So we're dividing both sides by that. Just to be explicitly clear, because I can. So we've got that. We're dividing both sides by that. And this cancels out all of that stuff on that side. Units included as well as numbers because, well, they canceled out. And so we've got the $60 divided by $3 per apple. Kind of a fun fact, when you have a denominator in a fraction that's the denominator of another fraction, it kind of comes up front when you up to the top, the numerator. So the x, this is in apples, and this should be 20 apples. Okay. So if I wanted to do a couple different steps, let's say someone's 6'8", that's how tall I am. 6'8". Let's try and turn that into centimeters and then meters. So the idea behind this is that we have something where we're going between inches and then centimeters. So we're converting that number of inches into centimeters. And then we're going to have to do the same thing with centimeters to meters. So when we're 6'8", that when you say 6'8" inches, that's equal to what's that, 80 inches? I think it's 80 because it's always so nice and neat for me. Because 6 foot Yeah, it's 72 plus another 8, so that's 80 inches. So we can say that, um, you know, let's start with our inches, and then we're going to go to centimeters, and then we're going to go to meters. And no, keep that lowercase. That's not how you write centimeters, man. So we know that at 0 inches, it's 0 for all that. Now, the conversion factor for this, if you have 1 inch, that should be 2.54 centimeters. And we can also convert that into meters, but we don't really need to do that right now. I know that also if we have 100 centimeters, that's going to be equal to 1 meter. We don't really need to fill in those other numbers as of right now. They're just kind of placeholders. Now, we know if we were to plug in these numbers and make this table really, really big, we can also say, okay, now I've got 80 inches. How many centimeters is that? And I can convert that into meters. So what this kind of looks like is if I have my 80 inches, I can multiply that by the conversion factor and get that into centimeters. So you can think about this as we said earlier, kind of like canceling out the units. So you can say inches and then centimeters. In 1 inch, we have the 2.54 centimeters. Now, you might be asking yourself, like, wait, why is this number going on the bottom, that going on the top? Remember, this is slope. And if we're converting between inches to centimeters, you should have that slope that has centimeters and inches in it. And so we should have something like this. Don't worry, I'll go over a little bit more of the explanation soon. So if we do that, we can convert that into, let's just get our calculator out. So we've got 80 times 2.54. That's our 203 point, what was it? 2 centimeters. And then you can convert that to 3.2 centimeters. And we can multiply that. So you've got your centimeters to meters. And in 1 meter, you've got 100 centimeters. So that's just a simple division problem. This should end up being 2.032 meters, which makes sense. I'm a little bit taller than 2 meters, by the way. You can also kind of skip writing this out. If you do something that looks like this, and then you multiply that by that as well. And this is the train car method or train track method. And you can just do all the math at once. So you take this times that, and you divide it all over this times that, and you can write it all out and do that all at once. So yeah, that's maybe, I don't know, I'm getting a little bit impatient. I might cut these. All right, now to help you understand a little bit of the math that's going on here, you guys know that if we have x and we multiply that by 1, it's still equal to x. So it's being multiplied by just 1 gives you the same thing. That's essentially what we've got going on when we're converting, but we're changing how we're looking at x. So x is no longer that type of thing, but it's going to be equivalent to it in some way, shape, or form. So you can think about this as x times what I like to say is like, it's kind of like a 1, but it's written differently. So I put little quotation marks around it. And that is going to give you something that's equal. So that, in this case, if you have the numerator and the denominator be equal to each other, so this is that numerator and this is that denominator, right? In that context, if the numerator is equal to the denominator, then fraction is equal to 1. Because it's like if you've got 10 over 10 or 5 over 5, right? So if we have 5 over 5, that's equal to 1. If I have 600 over 600, that is also equal to 1. So if we've got the same thing in the numerator and denominator, we haven't really changed the value because they're equal. So another way to think about this is this fancy looking one is essentially what we're using when we're doing slopes on our y-intercept equations. It also only works if your change in y is equal to or equivalent to the change in x. So if you've bought more apples, you're going to need to have a corresponding change in value. It's essentially saying like if you've changed this amount in your y, you've changed this amount in x, and they're equivalent or equal to each other in some way, shape, or form. So if we look at if you have inches to feet, you've got 12 inches is equal to 1 foot. And so this fancy looking one, in this case, instead of writing 12 inches over 12 inches, you can substitute a foot in there. So you can say like 12 inches and 1 foot. If you were to multiply something by this, it hasn't really changed its value. It's just changed the units that you're looking at. So if I said, okay, I'm 6 feet tall. I'm actually taller. We've gone over this. But let's say I'm 6 feet and I want to multiply that by feet to get to inches. It looks something like that. Sorry, my cat's behind me. And you end up having this fancy looking one. Remember, this whole thing is kind of like, it's a value of 1. So 6 feet is equal to how many inches? So 6 times 12, 72. So we can say that the like 6 feet, if we were to change this number and say 6 feet, that's equal to 72 inches, right? We could do the same thing with miles and hours. I'm just gonna grab this and move it over though for that. So let's work over here. So let's say that you're going like 60 miles every hour. And you want to know how much time has passed when you get to like 240 miles. And yes, you can do this math in your head. And you probably did that when you were in middle school math, right? But we got to be able to write this out, because if you can't, the longer problems are going to be very difficult. So if we've got like 240 miles and we multiplied that by its conversion factor, you can say, okay, I've got miles on the bottom and hours on top. Do you see how I'm always writing in the units first? That tells me what numbers go where, because I know sometimes people want to write the numbers first. I do the units first because I know I'm in miles and I'm going to need to cancel out miles. So we might as well start there, right? So we've got our 60 miles. That's equal to 1 hour. I believe that's 4, right? So that's 4 hours. So that's the idea behind a conversion factor. It's a fancy looking one. This is just a fancy looking one, and it allows you to take one unit and turn it into a different unit. Already in the video, I've talked about canceling out units a couple times, but what does it really mean? So I wanted to just go back and look at numerators and denominators and how we cancel out common factors with that. So if I had something like uh, 2 times 5 all over 5, I can cancel out the common factor, the 5 right here, right? So this is something that works for a lot of numbers. We can do this as, um, but it really all it is that you need a common factor between the two sides. Like if you had 2 times 3 times 5 all over 2 times 5, you can cancel out the 2's and the 5's and get just 3. And let's just work it out just to prove it to y'all. So we've got 10, and then we've got 2 times 3 is 6, times 5, that would be 30. Yep, that's my 3 right there. We could have canceled out our units right from the beginning right here and just get that. So when we're talking about canceling out units, it's the same idea as canceling out common factors. You just need to have it present in the numerator and present in the denominator. That's the main idea. So let's look back at a problem and show what I mean by this. If we look back at this, yeah, let's take that problem. Look at that here. We can say that we have, if we didn't cancel out the units, so I'm just gonna just get rid of the purple here real quick. We don't need that just quite yet. So we can say that this is meters times the centimeters all over centimeters here. And just like we did with the numbers, we can cancel out what's in the numerator and the denominator. This only really works when you use a conversion factor. You could multiply other numbers and then it wouldn't cancel, and then you'd be left with something that doesn't work. Like if I just put in, like if I put the centimeters up here and the meters in the bottom, I would get like centimeters squared over meters, and nothing's canceling out, so that can't be right. So that's one of the reasons that I encourage my students, sorry about that. That's why I encourage my students to always write in their units and to always physically cancel them out. Because when you start getting harder numbers that are a little bit more abstract, it can be pretty difficult to keep track of. Now, if we had something simple like, let's say, 24 inches, and we know that 12 inch is equal to 1 foot, I ask you how many feet that is, then we can do a simple conversion. And yes, I know you don't have to write it all out to do this one in your head. You can feel proud of yourselves for having this competency at this point. But, sorry, I just wrote in my number before I knew what units go where. Inches, feet, and then I want to do 12 inches and 1 foot there. And this is going to end up being 24 over 12. And this is like inches times feet all over inches. And then we can just cancel them out here. Just like how you could cancel out these numbers actually, and this is going to be 2 and 1 if you take out the common factor of 12. So it's 2 feet. Now, if you do something that's a little bit more abstract, like if you had like 2,000 molecules, and you're trying to figure out how many moles that is, Avogadro's number is a very abstract thing for most people. But I believe it's It's this. It's been a little while since I've done problems with that. But we've got that many molecules in 1 mole. So if we're trying to figure out this fraction, what you would do is you would take your units that you have, the molecules, and you would set up your conversion factor so that you have molecules on the bottom and you've got moles on the top. And in 1 mole, we have that many molecules. I'm lazy, so I'm just going to do that. And we should be able to do that on our calculators. Might take a little bit of time, but it is doable, and that should work for us. And we should be able to find the molecules because we can cancel out we can find the mole, the amount of moles here, because we're left with just mole. All right, time for the train tracks. So I really like this method, but it also can be a bit of a crutch for people if they just rely on it. So you have to kind of understand the math behind it. So if you haven't, I would encourage you to go back and watch other parts. But here's the main idea. This is something that you start off with, and then you're going to have, let's say, like that unit, and you convert between that unit to a different unit. And you can keep on kind of chaining these to combine multiple at once. So earlier, let's say this then goes to, I don't know, that will ultimately result in you just having the last unit that you converted by, because the rest of them should be canceled out. And a good example of this would be if we were to go back and look at the problem with this 2-step problem. So you can think of the train tracks as essentially being right here and there, just kind of cutting through the problem, and you get your final answer. So there's also this right here. These lines separate your conversion factors, and it's just a way of setting up your problems so that you know, like, okay, I've plugged something in, and you cancel out those units, and you cancel out those units, so on and so forth. That's the main idea with this. So if you wanted to do another problem like this, we can just set up our... All right, so let's say that you have some water at room temperature, and you've got a water bottle that can hold 0.75 liters, and you want to know how much mass that's going to be. So we're taking some volume of water and converting that into pounds using this density. They are also asking for the weight in pounds, and our conversion factor, if you've noticed, was given in grams per milliliter. So that's going to be an issue for us because we need to cancel out milliliters and work with grams. So we've got 0.750 liters. But if we want to turn that into milliliters, we need to cancel that out. So you see I've got my units. In 1 liter, there's 1,000 milliliters. And then I know that at this point, you could just work through that and get, if you were to do the equals sign here, you could get milliliters. But instead of doing all these little problems, we're just going to try and do it all at once. That's kind of what dimensional analysis is like doing a bunch of math problems, but all at once. And so we've got a density. So for every milliliter, we've got that number of grams. It's gonna, hold on. Let's get that right here. There we go. So if I did that math, then I would have just grams left over, and that's okay. But we want an answer in pounds, and so we have to know how many grams are in a pound. I need to look that up, actually. But once we have that, we should be able to just cancel out our units. So let me look that up and then we'll do the calculator. So I just wanted to highlight, because as I was going through these conversions right here, I actually started to write that number up there, but then I checked and I was like, wait, no, that's not my conversion factor. In 1 pound, I've got quite a lot of grams. And so just make sure you're double checking that as you go through this, and you should be okay. So if we did this math problem, we've got the 0.75 times 1,000. And then that times 0.998395. Okay, that's going to be that number. So we've got that to here. Now we need to divide that by 453.6. And we should get 1 point, what was that, 6 something pounds. And if we're doing our sig figs, which I also have another video on, this should be limited to 3 sig figs based off of what they gave us. Okay, well, that's that. That's our final answer. So you can kind of see how I went through and canceled those units. We'll do another couple ones to just demonstrate this a little bit more. So if we've got in 1 year, we're trying to convert that. So we've got in 1 year, we can say that that is 365.25 days because of the leap years, right? And then we're going to have our days to hours, and that should cancel out. So like how these years will cancel out, these days, because ultimately what we're saying is we've got some day in the numerator and some day in the denominator, so we can just cancel those out. This way, doing it earlier just kind of helps you keep track of what you've got so far. And then in 1 day, got 24 hours. And then in 1 hour, we've got 60 minutes. And then in 1 minute, we have another 60 seconds. And so it's a fair amount to cancel out. But you can see that this should work based off of what we've done so far. Sorry, I'm reusing colors. And then we're left with just seconds. So if we wanted to do this calculation, 1 times 365.25 times 24 times 60 times 60, and we get our final answer. Be careful when you're doing the calculator stuff, because a lot of times people will do some weird thing where they don't put parentheses around everything going in the numerator, and they start dividing stuff too early, and it messes up numbers. And yeah, you want to be careful with your calculator. So this is a pretty big number, which kind of makes sense. We've got, what would that be in scientific notation? 3.1, and we only had one significant figure, so it's about 3 times 10 up to what power? Okay, so we've got 1, 2, 3, 4, 5, 6, 7. 7. That makes sense. That's quite a big number. Quite a long amount of time in 1 year. So if you're trying to download, let's say, some game online, and it's a 100 gigabyte file, this is that gigabyte. Sorry, it looks like it's 6. If you have giga, that is, I just looked this up just a little bit ago, so I remembered it. Giga is 9. Mega is 10 up to the 6th power. So this is basically a million of whatever base unit, and this is basically a billion. So this is 3 magnitudes larger, or 1,000 times larger. In other words, there's $1,000 million in $1 billion. You can think about it like that. So we've got our gigabytes, and we could just go down to bytes, honestly. This is in 1 gigabyte, there's 10 up to the 9th power of bytes. And let's say that we're trying to convert using this megabytes per second. And so we've got our bytes to our megabytes. I think this is supposed to be a lowercase actually, but we're going to work with it. It's fine. So in 1 megabyte, there's 10 up to the 6th power bytes. There's a lot. And then we can do our megabytes to seconds. So in 1 second, it was 0.5 megabytes. So, because remember, 0.5 is the same as 0.5 over 1. And we can flip that here. So now we've got the denominator on the numerator and the numerator on the denominator. And that should work. So we've got that in seconds at this point. And that's almost as far as we need to go, because then we're going to go to seconds to minutes to hours to days, right? So there's that 60 seconds over 1. And then 60 minutes in hour. And then we've got that 24 hours. I'm running out of space. Oh, wait, I can scroll over. 24 hours. And that's equivalent to 1 day. And we can do that problem. It's kind of a big, nasty problem, but this is the idea, right? We're canceling out, so on and so forth. This is actually how fast my current internet is. Kind of slow. Takes me a while to download things. You'll see. It takes like days with the modern files that people are making. And that should cancel out all of our units, leaving us just with days. And so that should work. So we've got quite a long problem on the calculator here. This, I just know my base 10 rules is going to be 10 up to the 3rd. So it's going to be ultimately times 1,000, because it's going to be 100 times 1 billion divided by 1 million, divided by 0.5, divided by 60, divided by 60, divided by 24. So, yeah, it's a lot. I might skip showing the calculation and just get there, but I might not. All right, so the calculator, if we've got 100 and we times that by 10 up to the 9th power, we can get that number. And then we divide that by 10 up to the 6th power is 100,000. Remember, I had said that this should be effectively times 1,000. So 100 times 1,000 is 100,000. That sounds reasonable. Okay, so we're like right here now. Now we need to divide by 0.5. Okay, now we're there. Divide by 60. And that was just the first 60. Divide that by the second 60. And then divide that by 24. And it's a little bit more than 2 days. So 2.3 something days. 2.3, was it? 1 days. yeah, it takes a while to download a big game for me. All right. I think that's it. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about. And remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia. And if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.